Hello, this video will cover section 2.1, quadratic functions and models. Our three objectives will be to analyze the graphs of quadratic functions, also to write quadratic functions in standard form, and use the results to sketch graphs of functions. And then the third one will be to find the minimum or maximum values of quadratic functions in real-life applications. And these two words will come from the vertex. Okay, so this is the first section of chapter 2. We are going to have from 2.1 to 2.5 is about polynomials. The quadratic function is considered to be a polynomial of degree 2. And then in section 2.6, we will look into rational functions. Okay, so far in chapter 1, we focus on linear functions, and the equation that we use for it, perhaps in more familiar terms, we were using y equals mx plus b. So right here, when you see the a and the b, they're representing numbers. So that's what we call the linear function. And then we also looked at the constant function, which is also a linear function. However, we don't have an x term, or we do, it's just of degree 0. And so x to the power 0 is just equal to 1. So it's just like c times 1, which is c. And that is what we refer to as the constant function. The behavior of the graph is also constant, not increasing, not decreasing. And now we have here the parent function of the square function. Squaring function, or I prefer to refer to it as quadratic. Okay, and these functions are examples of polynomial functions. So right here, the linear function is a polynomial of degree 1 because that is the highest exponent. A constant function is of degree 0, and we have a linear function, a quadratic function, which is of degree 2. And they are part of the family of polynomial functions. Now, of course, we could have increase the degree. We could have degree 10, degree 100, and I mean, although they're not very common, but yes, as long as your x variable, your independent variable, has exponents that are either in fact, we could say we could use the word non-negative because we're including 0, where the exponents are non-negative integers. So we include 0, 1, 2, and so on. So all of those will be polynomial functions. So right here, if we consider, here we're going to generalize a polynomial. So far, if it's just a constant, it will be of degree 0. If it's a polynomial of degree 1, it will have those two terms, right? Or the constant term could always be 0 as well. So that would be a linear function. You could see the x is to the power 1. Now, if we want a quadratic function, of course, we will have the x squared. And then here the a sub 2 is representing the coefficient of the x squared term, just like the a sub 1 is representing the coefficient of x. And so if we continue and we look at the very first one that is here, a sub n times x to the power n, that will tell us which one is the highest exponent. So in this case, n is the highest or the largest exponent. And so for that reason, we say that this polynomial is a polynomial function, of course, of degree n, because that is the highest degree. N could be a 10, it could be a 9, it could be 100, as long as it is a non-negative integer. So as you could see, the second term from left to right is going to be x to the power n minus 1. So as you see, it's one less from n. And every term will follow the same pattern. The degree will go down by 1, and then the a sub n minus 1 is the coefficient that is attached to it. We're using the subscript to represent that is the coefficient for that particular term inside the polynomial. And let's see here. Let's just go over this. So we have a sub n is the coefficient of the x term with the highest degree or exponent. And so because of that, we refer to that one as the leading coefficient. And so that's going to be very important throughout this section and actually throughout the chapter. Leading coefficient and then the degree of the polynomial. Then you could see here a sub n minus 1 is the coefficient of the next term. And then the ellipses, the three dots in between, they just imply that there is a certain number of terms in between. We do not know how many because we don't know what n is equal to, but we know that the last three will be the one of degree 2. So we have the coefficient for that, and then the one with the degree 1, so we have the coefficient for that. And then, of course, we have our constant term, which is just the number, or we could also call it the coefficient of the x to the power 0. Now, since here we're saying that n is the degree of the polynomial, we don't want to say that a sub n is 0 because then that wouldn't be the highest x with the highest exponent there. So that's why we just make that little exclusion that one will not be equal to 0. All right, so again, here is just a little summary how the constant function, it is of degree 0. Degree 0. And then we have the linear function is of degree 1. And you can see here how this one it says that a cannot equal 0. I know that here it says that it cannot equal 0 for the constant as well, but I'm not really like agreeing with that statement because if we had the line y equals 0, I mean that would still be a constant function, but let's not worry about that too much. All right, so this section 2.1, we're going to focus on those polynomials of degree 2. So we will not be using all the stuff that you see on the left, but we will be referencing back to it in the following sections. So quadratic functions, they are polynomials of second degree. And we're going to look at some of the graphs for the polynomials that we see here. I'm going to go ahead and type them on Desmos, and then I will show you how they each look. Okay, so I have typed the functions, and I also included the parent function. The equation is here, y equals to x squared. So the first function from our slide is f of x equals x squared plus 6x plus 2. So we have the graph right here. And you could see that it's still opening up, but it was shifted from the parent function some units down and some units to the left. Okay, now let's look at the next one. G of x, that one it's still opening up, and it was shifted 3 units down and 1 unit to the left. You could see that from the vertex, instead of being at the origin at 0, 0, we have this one here at -1, -3. Also, because of the 2 here, it's doing a vertical shrink. So, oh no, not a shrinking. Oh my gosh, I can't think of the word. stretch, a vertical stretch. That's what's going on. Okay, now let's look at the next one, h of x. And you could see that one. I'm going to just adjust this. It was shifted so many units up, I believe 9 units up. You could see that right here with a 9. And then the 1/4, it did like a horizontal extension. I'm sorry, stretching, or we could actually, this will be better. It is a vertical shrunk because we're multiplying by 1/4. Okay, next one we have k of x. Now this one, you notice we have a negative here in front of the x. -3 is the coefficient, the leading coefficient. So that means that the function, it was reflected from the parent function, reflected across the x-axis, and then the vertex was shifted 4 units up. Well, not just the vertex, but every single point. And so that's why you see the reflection and then the shifting up from the parent function. Okay, and then let's look at this one here, m of x. And as you can see, we have it in factor form. But if we were to expand those two binomials, if we were to multiply them, we will see the equation will be x squared minus x minus 2. And so here is the graph for it. So this is a nice thing. You could graph like that on decimals. You could also graph like that on a calculator. You could leave them in factor form and it would still work out. Okay, so the formal definition, and also we have here what we call the standard form of the quadratic equation. And so here, let's just notice that A, B, and C are real numbers. They're not variables. And since we're saying this is a quadratic, we don't want the leading coefficient, which is A, to be equal to 0, because then it wouldn't be a quadratic function. So we will be either talking about a linear or a constant function, depending on what B is. But we just want to make sure A is not 0 because we want it to be quadratic. So that is the quadratic function, and the shape of this type of functions, they're shaped like a U, and we refer to them as parabolas. And so parabolas, they do actually occur in many real life applications, um, especially those involving reflective properties of, for example, satellite dishes and a flashlight reflector. And if you were to form a parabola shape it into a 3D, uh, it's not like a very good example, but it could be something like a satellite dish, or it looks more like a boat, like those dish network things. A flashlight, for example, the inside of a flashlight, I'm not drawing very good right now. The inside of it, it is shape like a parabolic 3D object. And actually, where you place the light of the flashlight, it has a lot of importance because it will give you the maximum power, and it reflects around the parabolic dish, and this one too. You will learn more about that, not in this chapter, but if you take the second part of pre-cal, we studied that in chapter 10. Okay, so right now we're going to focus only on 2 types of parabolas, and these are the ones that are actually functions. And we know that to test if they're a function, we could draw a vertical line test. It will pass it, obviously. So that tells us, yes, they are functions. So we're going to classify them into 2 cases. The one that is opening upward, like that, and that is because the leading coefficient is positive. So here we're calling it A. So we're going to say A is greater than 0. That's to be positive. And then we have the other case, which will be opening, well, let me highlight right here. The other case, opening downward. And that will happen because the leading coefficient, the a, is negative. So in other words, a is less than 0. Oh, we also have that here. Okay, so now if we have a parabola that is opening upward, and by the way, just to remind you, the domain is all real numbers. So if the parabola is opening upward, what that means is that the vertex of the parabola is actually the lowest point. And if it is the lowest point, we refer to it as the minimum. In fact, I'm going to write it as a point because the minimum is the actual y value. That's what we call the minimum, and it will be the minimum range or output that the function will have. So if we have a parabola that is opening downward, then the vertex is going to become the highest point. And so because of that, we refer to that as for some x value, and then the y value will be the maximum. So that's very important to remember because a lot of the applications have to do with the vertex. And so right now, identifying if the parabola will open up or down, it's very important, and remember that comes from the leading coefficient, whether it is positive or negative. I tell my students they can remember like this: positive people are usually smiling, negative people are usually frowning. Okay, so if the graph of the parabola that has the vertex at 0, 0, which is at the origin, we already know that. And if a is greater than 0, as we could see here, we will have the parabola opening upward. And so same things, the minimum value will be the y value, 0. And that is if the leading coefficient is positive. So this is the same as the previous slide, but here we're not working with any type of transformations like a shift. Um, However, here we have the one with the leading coefficient negative, a is less than 0, and so we see the parabola opening downward. So it is the same thing. And in this case, the y value is the maximum. For the other one, it was the minimum. So make sure you do remember those words. And just to remind you, the maximum here is the y value. Okay, here we have to, for example 1, sketch the graph of each quadratic function and compare it with the graph of y equals x squared. So we have y equals x squared, which is our parent function. We know that already. And so if we have 1/3 of x square, this 1/3 is actually causing the graph to have a vertical shrunk or compression. And then the one that has the 2, if we compare it again to the parent function, is the parent function is the one I'm highlighting in yellow. And so the transformation, which is 2x, that will be a vertical stretch. Stretches the parent by a factor of 2. And for the other one, it will be a vertical shrunk or shrinking. In example 1, we went over how the coefficient a determines how wide the parabola f of x a equals ax squared opens. So when a is small, and we're going to use the absolute value because a could be positive or negative. So if a is small, the parabola opens wider than when a is large. And so you could see here how a was smaller than 1, it's 1/3. So it makes the parabola appear wider because it's also being shrunk vertically. Now, when that value of a is greater than 1, then the parabola will stretch vertically, also making it appear narrower. Okay, so this is a summary of the transformations. We cover this in section 1.6, and we have here the very first is the horizontal shift. And remember, that is counterintuitive. So if you see a plus C is moving to the left, minus C is moving to the right. Then we do have the vertical shift. And that one is self-explanatory. If you have a plus, a constant, it moves up, minus a constant, it moves down. And then we have the two types of reflections. And right here, this one is going to be the reflection across the x-axis. In other words, when the leading coefficient is negative, less than 0. And then for the other one, this is a little interesting because the negative is placed inside the parentheses. So by definition, this represents a reflection across the y-axis. However, a parabola is symmetric with respect to the y-axis. So even if we turn that parabola, let's say that this right side it's yellow and this other side, let's say, is blue, right? So if we rotate that across the y-axis, it will just be the yellow will now be here, and then the blue will be here. If we rotate it across the y-axis again, then the colors, the two sides will just rotate, but since they are the same due to the reflection, then we can't really see a difference with those types of reflections. Okay, so right here we have two more examples. We have, and you can see again how the parent function is here so that you can keep track of what's happening with the transformations. And so we have the function negative x squared plus 1. And so you could see that the negative is giving that reflection across the x-axis. And then the plus 1 is moving the parent function upward shift of 1 unit. And then with g of x, we have the equation there. And so what's happening is that we have a shift left 2 units. That's the plus 2 inside the parentheses. And then we have a downward shift for 3 units. That is the minus 3. So 3 units down. And then the plus 2 is 2 to the left. Remember, horizontal shifting is counterintuitive. So the vertex from being at 0, 0, it actually moved to -2, -3. And you could see the point right there. And by the way, this is a form, another form of the parabola. It's called vertex form. Oops, I dropped my mouse. Everything's okay. Okay, so let's go to the next slide. Okay, now this kind of bothers me a little bit because this is called vertex form, and here this book is referring to it as standard form. So let's just go by the book and call that standard form. And but just keep in mind that other books refer to it as the vertex form. And the reason for that is that you can identify the vertex just by looking at it. And that vertex comes from the constants that you see here, h and k. So h is the horizontal shift of the vertex, and k is the vertical shift of that vertex. And so that is what we call standard form. We're gonna say the same things about a, the leading coefficient. So if a is positive, the parabola opens upward, and if a is negative or less than 0, the parabola will open downward. And so here, another thing to consider is, and I didn't mention earlier, is that when the parabola is shifted, like the example that we see here, it's not symmetric with respect to the y-axis anymore. However, it's still symmetric with respect to its own axis of symmetry, which is this line that I'm highlighting with pink. And that line, since it is a vertical line, is going to have an equation like x equals to a number. And that number, it just happens to come from the vertex, the x coordinate of the vertex. So that is going to be the line that the parabola or the quadratic function is symmetric with respect to, meaning that you can fold your parabola right along the axis of symmetry and you will have the exact same thing on both sides. Okay, so that is the axis of symmetry. Let's highlight that. The vertical line, x equals h. And remember how it will be this the h that comes from the vertex. So if the vertex is h comma k, x equals h is the axis of symmetry. Now, it's important to notice how we have a negative sign right here. That is part of the standard form of the quadratic function. So another reason why the horizontal shifting of the vertex will be counterintuitive. So if you see something like, let's say y equals x minus 3 squared plus 4, something like that, then the vertex, we only consider the number 3, not the minus. So we use a positive 3. This one, we just keep the sign like it is, like that. But if we were to have another one, I'm going to write it here. That was y equals x plus 4, let's say that. And then let's put a plus 4 here. So then the vertex will be equal to, if we see a plus 4 here, we got to use negative 4, the opposite number, and then the vertical shift is just stays like that, like it is. And the reason for that is that the plus that you see here is actually a double negative that is happening. So this double negative is what causes that positive symbol to be there. Okay, so to graph the parabolas, it's helpful to begin by writing the quadratic function in standard form. So we could go from general form to standard and vice versa. So again, general is the one that I think I called it standard, but let's call it general. I don't agree with this, but that's fine. Um, so f of x is equal to ax squared plus bx plus c, and standard or vertex form that will be the a and then x minus h squared plus k. So to go in this direction from general to standard form, we will use the completing the square. And then to go from, let's say, standard to general, actually, yeah, from standard to general, and the other one goes like in this direction. So from general to standard. So for that, we will expand, or in other words, we multiply. Square it, and then distribute the a, combine like terms. So we do that. So let's see how it will work first to go from, and I mean, why would we want to go from general form to standard form? Well, because the standard form tells us the vertex right away. So that's why it is useful. Remember, it comes from here and here. So to complete the square, here are some steps that you could see here. It's not very well explained. So let's work this example 2 together. Okay, so for example 2, we're going to sketch the graph. We have the equation right here. And we are also going to identify the vertex and the axis of the parabola. The axis of symmetry, we should say. Okay, so to sketch the graph, and I told you we were going to do that by using this process. So to graph a parabola, it's helpful to begin by writing the quadratic function in standard form. So that is what we're going to be doing by using the completing the square process. So what we do first is I'm going to rewrite the parabola here, but I am going to leave a little space. Well, actually, what I'm going to do is combine these two terms, not really combine them because they're unlike terms, but I'm just going to group them. And then I'm still going to have my plus 7 here. Okay, from here, what I need to do is the only way that I can use the completing the square method is if the leading coefficient is a 1. So what I need to do, I need to factor out the 2. So I will get x squared, and if I factor 2 from 8x, it's like 8x divided by 2, so it is 4x. Okay, now after that, we are going to leave a little bit of extra space here inside the parentheses. And we're going to use a term that will go there. Okay, so now where's that term going to come from? Well, it's going to come from half of this number. So half of 4. So 4 divided by 2 is 2. And then we're going to square it. Okay, then here we're going to need to enter a number as well. But that number is actually going to come from, and actually let's hold on that number for a second. So it will be 2x squared plus 4x plus 4. That's the number that we enter, a plus 4. And then outside the parentheses, we have the plus 7. The 7 was here. And now what I'm going to do, instead of adding it, like I said here, I am going to subtract it. So if it was a 4, I'm adding a 4, I will subtract 4, and it's like positive 4 minus 4 is 0, so it's like I added 0 the whole time. However, I don't need to subtract a 4, because what I did here is I factored out the 2, so then the number that I am actually adding is the product of the number that I factor out times 4. So 2 times 4 is equal to 8. So if I added 8, that's in reality what that is, because the 4 is inside the parentheses. And so I need to subtract 8. So you need to add and subtract the same number, so that in reality you're just adding 0. Okay, so now that we did that, we are going to factor the trinomial into a binomial square. And so that is the purpose of completing the square, so that we can factor it in this way. And the factoring will be x plus, and actually that's why I like to use this and have like a 2 square there, because that positive 2 is actually telling me what I'm going to include here, plus 2. And then we could combine like terms here. So we have a plus 7 minus 8. So that is a negative 1. Now that our quadratic function is written in vertex form or standard form, we could find right away what the vertex is. And that is going to come from here. We see a plus 2, so we have to use a minus 2. And then we see a minus 1, so we still use a minus 1. Okay, the axis of the parabola, or the axis of symmetry, is going to come from the x value. X equals negative 2, and it is a vertical line, so that's why we use that. What else can we do? Well, we could also find, and this is one of the nice things about having an equation in this form, that in general form, that if we need to find the y-intercept, for example, let's do that. We will find f of 0. And so I'm going to just use the parabola, the equation, but I'm going to replace the x's with a 0. Remember, for a y-intercept, the x will be 0. And so we have 2 parentheses 0 square, and then I believe we had a plus 8 parentheses 0, and then a plus 7. So you could see here that 0 squared is 0, times 2 is 0, 8 times 0 is 0. So all we have left is a 7. So that tells me that the point that will be on the y-axis is going to be 0 for x, remember that is by default, and then 7 for the y. So to graph something on WeatherTime, I believe you only need 2 points. Now, if they ask you to graph the axis of symmetry, make sure you graph the vertical line, but also make that line dash or dotted. And if you have issues graphing on WebAssign, please contact the online tutoring because I do not know how to graph on WebAssign. I have never used WebAssign as a student, so I never had the need for it. I can graph by hand. I can actually draw pretty nice graphs, but not not on WebAssign. So let's just graph it, and I'm like running out of space. Actually, I guess we could graph it here. All right, so far we have the vertex was at -2, -1. So we could place it there. Also, the leading coefficient of this parabola is a 2, +2. So because A equals 2, which is greater than 0, positive, this is gonna be opening upwards. So from this vertex, we will have something opening up. Okay, now that is the, let's graph the axis of symmetry, which is the line x equals -2. And this is what I was talking about of making it dash or dotted. Because if you make it solid, you're saying it's part of the graph, and it's not really part of the graph. The only part of the graph will be the solid parabola. Okay, we also found the y-intercept right here, 0, 7. So let's see, 1, 2, 3, 4, 5, 6, 7. So we could plot it here. And then perhaps let's get another point. In fact, let's go ahead and find the x-intercepts. So to find the x-intercepts, since these are points that will have 0 for the y, that is our first step. We let y equal 0. Or in other words, we let f of x. Remember, f of x and y are both used for the output, so we let that equal 0. So if we use our same graph we had a 0, it's here. F of x equals 2x squared plus 8x plus 7. 2x squared plus 8x plus 7. And we could try to factor it since we're equaling one side to 0. And let's see if we can factor it. So the only way to get 2x squared will be by multiplying 2x times x. And then the only way to get a plus 7 is by multiplying +7, +1, or -7, -1. But because all the signs are positive, that tells me that everything will just remain positive. So let's see if we could do this. If we have a 1 here and a 7 here, let's check this. We will get 2x times 1 is 2x, and then 7x times 1, it is or what am I doing? Okay, yes. 2x times 1, and then 7 times x, 7x. If we add them, we will get 9x. So it is not factorable. So then what we will have to do to find the x-intercepts will be to use the quadratic formula. And quadratic formula is the one that looks like this: -b plus minus square root of b squared minus 4ac over 2a. And so to do that, we will have x is equal to b is positive 8, but the formula requires a negative 8, so we have to include that there. And then plus minus square root, b squared will be 8 squared. Then minus 4 times a, which is 2, times c, which is 7. Everything divided by 2a, so 2 times 2. Okay, so we will get negative 8 plus minus square root of 64 minus 4 times 2 is 8. 8 times 7 is 56, and everything divided by 4. Okay, so 64 minus 56 is equal to 8. So now we have x is equal to negative 8 plus minus the square root of 8 and then divided by 4. Okay, so one thing that we could do here is factor the 8 inside the square root. So to get a more exact solution, so that would be 4 times 2, that's 8. And then we could take the square root of 4 and take that out of the square root, so that will be 2, that's the square root of 4. And then the other 2 will remain inside the radical, and then divided by 4. So the value here is going to be, if we simplify it a little bit, negative 8 divided by 4, that would be negative 2. And then plus minus, if we divide 2 by 4, that will be 1/2, or we could just say the square root of 2 over 2. Now, if you want to know the value of that, and remember the plus minus means 2, so I'm going to just enter this on the calculator. So I get approximately negative 1.29, and the other one will be negative 2.7. So those numbers will be maybe somewhere here, and then for the, if that's negative 1, negative 2, negative 3, so the other one will be like somewhere here. All right, and so now I'm going to connect the vertex with the x-intercept, and then with the y-intercept, of course. And then remember, it's symmetric with respect to the axis of symmetry, so it's going to look like something like around that. All right, so that is the parabola, and of course you could use your calculator, you could use decimals, but whenever you're asked for an exact answer, you know, on WebAssign they imply those type of answers, the ones with the radicals and fractions. Now, if we had been able to factor it, it could have been so easy to find the x-intercepts, because then you just take each factor, equal it to 0, and then you find your x-intercepts, which are also the roots of the equation. Okay, so we're done with that graph. And of course, this arrows here, I was just showing the behavior. Okay, now what if we don't want to do all this completing the square? It is kind of tedious. So Another way to find the vertex when you have something written in the general form this way, instead of converting to vertex form, we are going to use the coefficient A and the coefficient B to find the coordinates of the vertex. So remember that point, the vertex, it could be talking about the minimum value or the maximum value, all right? Depending if the parabola opens, if A is positive, it opens upward. So the vertex is considered to be the minimum value. Remember, we did some examples. So if it opens upward, the vertex is the minimum value. And if the parabola opens downward, if A is negative, the leading coefficient, then the vertex is considered to be the maximum value, like so. And remember, I told you that those are the actual y values. Now, what is the y value? Well, it's actually the function value, the ones that you see here. Those will be either the minimum or the maximum. Now, the x value of the vertex, remember, this is the x, this is the x, this is the y. And so the x value is where it actually happens at x equals blah, blah, blah. And then the y value is going to be either the min for minimum or the max for maximum. Now, what is the negative b over 2a? Well, the negative b will come from the coefficient of x, and the a is going to come from the coefficient of x squared. Now, with that, we're going to find the x value. Once we have the x value, as you can see here, we have f of that value. And that is because for each x, there is a y. So we're going to substitute the x value found into the function, and that is how we're going to get the output of the vertex. The output, so let's number our steps here. First, we find x coordinate of the vertex by substituting negative b over 2a. That's going to give us a number. And then second, you substitute x coordinate negative b over 2a into f of x. So in other words, you're finding, instead of x, you replace that with whatever number you found from here, from x. So here we just say f of negative b over 2a, so we can generalize it. But in reality, you will be substituting a number, so it will become quite easy. So let's see that with our last example of this section. So it says the path of a baseball after being hit is given by the function f of x, and then we have the equation. So I'm just going to rewrite it here. Negative 0.0032 x squared plus x plus 3. Now, it says here where f of x is the height of the baseball in feet and x is the horizontal distance. So we have x horizontal distance and f of x or y is the height or vertical distance. And the question is, what is the maximum height of the baseball? So first, we're going to identify our A. A is here. And our B, which is here. Oh, no. Oops. B is the coefficient of X. So B is just 1. Now we're going to use the formula negative B over 2A. And so that will be negative 1 over negative 0.0032. So you notice we have two negatives. Oh, and actually, what am I doing? I did not use the 2 times B. I'm so sorry. I'm just excited because this is our last problem. Okay, so this is negative 1 divided. I'm going to go ahead and multiply this. So it will be negative 0.0064. Now I'm going to go ahead and divide because I'm dividing two negative numbers. I am going to get a positive. Okay, so I substituted. Remember, first I had to multiply this 2 times that. I got that number, then I divided because there are two negatives, I get a positive. And I just put that in the calculator. 1 divided by 0.0064, I got 156.25. That is the x coordinate of the vertex. Okay, now step number 2 is to find the y coordinate of the vertex. So then we're going to use f of the number we found for x. So 156.25. And so what are we going to do with that? Well, we're going to substitute that. This number here, we're going to substitute it where we see an x, there and there. So this is going to look like this. Negative 0.0032 parentheses 156.25. We have to make sure we square it. And then plus 1 times 156.25. And then plus 3. Okay, so what I get from here is equal to 81.125. And so that's going to be the maximum height. Remember how A is negative, so that means the parabola is going to open downward. And so the vertex is going to represent the maximum, of course, horizontal distance. Actually, not the maximum horizontal distance, only the maximum height. So that is the vertex. So the question is, what's the maximum height? The maximum height is here. That's the maximum height. And this number here, it represents that it's happening, or the baseball is achieving its maximum height at the x value, or horizontal distance, 156.25. Okay, so this is the end of the video.